Okay, we've gotten through chapter 1, so we're moving on to chapter 2. Chapter 2, we're going to talk a little bit more about the origin and the basic composition and structure of the atmosphere. We're going to look at atmosphere in broad terms here. So, with that, what is the composition of the atmosphere and the structure? Well, the weather has a lot of interesting pieces to it, and the atmosphere is all interrelated. So, in other words, what's happening over in Africa actually has an impact on the U.S., or maybe the U.S. has an impact on Europe. So, what we are doing here, we're looking at a picture of dust in the atmosphere. You see it here. It's a satellite image of dust, basically showing the gray, the yellow, the more dust. It's coming off the Saharan desert. In the summertime especially, it moves from there and across the Atlantic, the southern part of the Atlantic. And this dust layer actually impacts tropical storm formation. Where there's a lot of dust, there's not much in the way of tropical storm formation. And this dust actually can be seen all the way in. It has gone into the eastern parts of the United States. I have seen it come in to the Carolinas, even into Virginia, and visibility is reduced down to less than a mile sometimes in this dust. This past summer, we've been dealing with a lot of smoke coming down out of Canada. Again, atmosphere moving around air. That smoke would come, origin of that smoke was up over Quebec, Ontario area. And it would, every time we had a northwest flow, it would come down. I got tired of it at my house, and I'm sure you got tired of it at yours as many times. So, weather can go instantly, it seems like almost, from a beautiful day to not so nice. So, the atmosphere is really thin. All right, half of the mass of the atmosphere is within 18,000 feet, a little bit over 3 miles. So think about it. A lot of you guys might be able to run 3 miles. I can't necessarily anymore. I never could real well. But we'll say if you did, that's not that far. So you basically, if you could all run up in the vertical, you would cover through half the atmosphere in 3 miles time. 99% of it within 20 miles of the Earth. So again, this little layer that surrounds the Earth that we need to live, the atmosphere, is fairly thin. The Earth's system is made up of the atmosphere, the hydrosphere, which is just water, the geosphere, that's things like rocks or volcanoes. The biosphere is the plants. The lowest part of the atmosphere, the percentages of each gas are literally the same. In other words, if I am at the Earth's surface or all the way up on top of Mount Everest, 78% of the atmosphere at that location is nitrogen. Now, there's a lot less molecules up there on the top of Mount Everest than there are down at the Earth's surface. So yes, I'm going to have a harder time breathing up at the top of Mount Everest than I do at the Earth's surface. But that same percentage is 20%, almost 21% is oxygen. So there you can see the different parts of percentages. There's also aerosols. I showed you some dust that gets there, erosions from soil, ocean spray. Water vapor is something else that goes in the atmosphere and makes up. It can be fairly significant in the lowest 1 kilometer. Clouds and all bring the moisture even higher than that. But it might be up to 4% volume in the lowest 1 kilometer of the atmosphere. Carbon dioxide, definitely needed for life. However, too much of a good thing can be a problem. But it is needed by all the plants, which then make it into oxygen for us. And both CO2 and water vapor are going to be what keeps our atmosphere warmer than it otherwise would be. Pollution can be man-made. I can remember growing up and driving through Pittsburgh and looking at what I thought was wow, this place you can hardly see. And this was back in the 60s. But things have gotten better. We have learned to deal with pollution much better and improve air quality. Scientific methods. I'm going to describe a case that I happen to deal with. Worked with North Carolina State University on a project. Interestingly, when thunderstorms develop out in Ohio, West Virginia, and move into the Appalachian Mountains, sometimes they move on across and they just maintain their intensity and just roar right on through Virginia, North Carolina, that part of North Carolina that's on the east side of the mountains. Other times, they weaken and maybe even dissipate. And we think we knew something about this, but we always had questions. So we formed a hypothesis. The question was asked, what makes them? The hypothesis we made was you need a certain amount of instability to have this happen. Instability is something we'll talk about later. So if that was the case, then we reach a certain threshold, then we would believe the thunderstorms would continue on across eastern Virginia. So we went back and examined this and did an analysis. We wound up, we had to adjust that threshold. But eventually we were able to say, okay, at this point, most times, thunderstorms are going to increase literally when they come across the mountains. So instead of weakening, we would know we would be getting more. And that's how you do a scientific method to figure out that. We also look at models of the atmosphere, such as a vortex chamber, numerical models. Numerical models can be quite complex because, as you're going to discover, there's a lot of variables and they're always changing. And yes, we have an issue. No mathematician, nobody can solve the equations that describe the atmosphere. So with that, we're approximating. Yeah, we're getting better and better approximations, but we're still approximating. Numerical modeling is what I did in grad school. I also used numerical models when I was forecasting the weather. Automated surface observing system. Every airport in the country has one of these. They are literally every minute or faster recording a complete set of data on what is happening at that location as far as weather variables. So that is telling you the temperature, visibility, clouds, wind speed, direction, all of that every second. So that is then being able to be transmitted to weather service offices, other observers, pilots. And that's the reason it's at the airport is pilots need to know this. They cannot take off or land without really understanding what the weather is right where they are. There's a cooperative network, basically is more climate focused. And CocoRa's. CocoRa's is all volunteer, but it's a great network for precipitation. Maybe even hail, snow. It is a great way meteorologists will use it to draw a map of snowfall over an area or rainfall over an area by getting these volunteer reports. Radiosondes. All radiosondes are is a big balloon with a lot of lighter than the surrounding air gases. It's usually helium. It used to be hydrogen, believe it or not. And they go up until they break. And then they come back down with a parachute. But the measurements are taken on the way up. So this is giving you a vertical profile, literally, of the atmosphere. A dropson. There's another method of this, of just being dropped out of an aircraft. It's used a lot of time in Hurricane Hunter aircraft, but it can be used in other aircraft. Actually, there are aircraft that fly into storms in the wintertime, extratropical winter storms, and drop these kind of instruments over the ocean just to see what's going on and give another facet of data. Radar, great source. There are 122 offices in the United States with radar, and each one provides a map of reflectivity, which is looking at the precipitation that's falling. They also provide wind direction, and you can infer speed and all from that. And they can tell you, because they're dual pole, which is something new now, they can actually tell you the shape of the droplet or particle they're examining. And this can be useful in determining things like hail. And here you can see the different temperature profiles. Notice temperature is always dropping in the troposphere as a standard rule of thumb, and then gradually rising in the stratosphere, then dropping in the other one. Basically, the temperature change, how the temperature is behaving, defines each layer. And finally, auroras are just caused by the solar wind. So one last thing I was just going to show you, I wanted to give you a little quick peek. We talk about upper air. Here's this all taken from that radio sign. This is a Stuvie diagram, and you're going to see these in your book. All it is, y-axis pressure, x-axis as a temperature. Now, a dew point is a temperature. So that is a measure of moisture. So it plots a dew point, it plots a temperature. The closer they are together, the more moist the atmosphere is, closer to being a cloud. The further apart, the drier the atmosphere is. And here are the winds that go along as you go up or down there as well. And you can see, if I told you that I had a stratiform cloud here, I'd probably be moving towards the east. Oh yeah, if I had them up here, I'd probably be moving towards the southwest or south. So you can see clouds move in different directions. Now, I wanted to give you just a quick look at another interpretation of an upper air sounding. Notice the temperatures and dew point. This sounding, however, gives you a much better, clearer way of looking at how unstable the atmosphere is, which is going to be something you're going to discuss later on. So we're going to be talking a little bit more about SQ-Ts. And instead of plotting the atmosphere in the straight up and down with temperature, they're actually at a 45-degree angle. They're skewed. That's why it's called SQ-T. So I hope you got a little bit out of this, and please don't hesitate to ask if you have any questions.